Section 1.1, An Introduction to the Whole Numbers. In this video, we will learn the definition of a whole number and how to graph numbers on the number line, how to order the whole numbers, how to write whole numbers in expanded notation, how to round whole numbers, and how to read whole number data in graphical form. 1.1, An Introduction to the Whole Numbers. A set is a collection of objects. If the set is finite, we can describe the set completely by simply listing all of the objects in the set and enclosing the list in curly braces. For example, the set is the set whose members are dog, cat, and parakeet. If the set is infinite, then we need to be more clever with our description. For example, the set of natural numbers, or counting numbers, is the set. Because this set is infinite, there are an infinite number of natural numbers. We can't list all of them. Instead, we list the first few, then follow with 3 dots, which essentially mean etc. The implication is that the reader sees the intended pattern and can then intuit the remaining numbers in the set. Can you see that the next few numbers are 6, 7, 8, 9, etc.? If we add the number 0 to the set of natural numbers, then we have a set of numbers that are called the whole numbers. The whole numbers will be our focus in the remainder of this chapter. Graphing numbers on the number line. It is a simple matter to set up a correspondence between the whole numbers and points on a number line. First, draw a number line, then set a tick mark at 0. The next step is to declare a unit length. The remainder of the whole numbers now fall easily in place on the number line. When asked to graph a whole number on a number line, shade in a solid dot at the position on the number line that corresponds to the given whole number. For example, if you want to graph the whole numbers 1, 3, 5 on the number line, shade the numbers 1, 3, and 5 on the number line as solid dots. Ordering the whole numbers. Now that we have a correspondence between the whole numbers and points on the number line, we can order the whole numbers in a natural way. Note that as you move to the left along the number line, the numbers get smaller. And as you move to the right, the numbers get bigger. So, to the right of 3, we have 4, 5, and 6, which are larger, and to the left of 3, we have 0, 1, and 2, which are smaller than 3. This inspires the following definition. Ordering the whole numbers. Suppose that A and B are whole numbers, located on the number line so that the point representing the whole number A lies to the left of the point representing the whole number B. So if A were 3, B would be 4, 5, or 6. And if B were 3, A would be 0, 1, or 2. In this example, the whole number A is less than the whole number B. And alternatively, the whole number B is greater than the whole number A. Written these ways. B is greater than A is less than B. Comparison property. When comparing two whole numbers, A and B, only one of 3 possibilities is true. Either A is less than B, A equals B, or B is less than A. Example 2. Compare the whole numbers 25 and 31. Solution. On the number line, 25 is located to the left of 31. Therefore, 25 is less than 31, and we write it as 25 less than symbol 31. Alternatively, we could also note that 31 is located to the right of 25. Therefore, 31 is greater than 25, and write it as 31 greater than symbol 25. Expanded notation. The whole numbers, 0 through 9, are called digits and are used to construct larger whole numbers. For example, consider the whole number, pronounced 222. It is made up of 3 2's, but the position of each 2 describes a different meaning or value. The first 2 is in the hundreds position and represents 2 hundreds or 200. The second 2 is in the tens position and represents 2 tens or 20. The third 2 is in the ones position and represents 2 ones or 2. Consider the larger number. The following table shows the place value of each digit in this larger number. In expanded notation, we would write 100 million plus 2 10 millions plus 3 millions plus 400 thousands plus 5 10,000s plus 6 thousands plus 7 hundreds plus 8 tens plus 9 ones. We read the numeral as 123,456,789. Let's look at another example. Example 3. Write the number in expanded notation, then pronounce the result. Solution. In expanded notation, the number becomes 2 10,000s plus 3 thousands plus 7 hundreds plus 1 10 plus 2 ones. This is pronounced 23,712. Example 4. Write the number in expanded notation, then pronounce the result. In expanded notation, the number becomes 200 thousands plus 0 10,000s plus 3 thousands plus 4 hundreds plus 0 tens plus 5 ones. Since 0 10,000s is 0 and 0 tens is also 0, this can also be written 200 thousands plus 3 thousands plus 4 hundreds plus 5 ones. This is pronounced 203,405. Rounding whole numbers. When less precision is needed, we round numbers to a particular place value. For example, suppose a store owner needs approximately 87 boxes of 10-penny nails, but they can only be ordered in cartons containing 10 boxes. Note that 87 is located closer to 9 tens or 90 than it is to 8 tens or 80. Thus, rounded to the nearest 10, 87 approximately equals 90. The store owner decides that 90 boxes is probably a better fit for his needs. On the other hand, the same store owner estimates that he will need 230 bags of peat moss for his garden section. Note that 230 is closer to 200s or 200 than it is to 300s or 300. The store owner worries that might have overestimated his need, so he rounds down to the nearest hundred. 230 approximately equals 200. There is a simple set of rules to follow when rounding. Rules for rounding. To round a number to a particular place, follow these steps. 1. Mark the place you wish to round to. This is called the rounding digit. 2. Check the next digit to the right of your digit marked in step 1. This is called the test digit. If the test digit is greater than or equal to 5, add 1 to the rounding digit and replace all digits to the right of the rounding digit with zeros. If the test digit is less than 5, keep the rounding digit the same and replace all digits to the right of the rounding digit with zeros. Let's try these rules with an example or two. Example 5. Round the number to the nearest 10. Solution. Mark the rounding and test digits. The rounding digit is 6. We want to round to the place value of 6. The test digit, the digit that comes after the rounding digit, is 9. The test digit is greater than 5. The rules for rounding require that we add 1 to the rounding digit. Then make all digits to the right of the rounding digit zeros. Thus, rounded to the nearest 10, 8,769 approximately equals 8,770. Mathematical notation. The symbol squiggly equal sign means approximately equal to. Example 6. Round the number 4,734 to the nearest 100. Solution. Mark the rounding and test digits. The test digit is less than 5. The rules for rounding require that we keep the rounding digit the same, then make all digits to the right of the rounding digit zeros. Thus, rounded to the nearest 100, 4,734 approximately equals 4,700. Tables and graphs. Reading data in graphical form is an important skill. The data in Table 1.1 provides measures of the carbon dioxide content, CO2, in the atmosphere gathered in the month of January at the observatory atop Mauna Loa in Hawaii. In Figure 1.1a, a bar graph is used to display the carbon dioxide measurements. The year the measurement was taken is placed on the horizontal axis, and the height of each bar equals the amount of carbon dioxide in the atmosphere during that year. In Figure 1.1b, a line graph is used to display the carbon dioxide measurements. Again, the dates of measurement are placed on the horizontal axis, and the amount of carbon dioxide in the atmosphere is placed on the vertical axis. Instead of using the height of a bar to represent the carbon dioxide measurement, we place a dot at a height that represents the carbon monoxide content. Once each data point is plotted with a dot, we connect consecutive data points with line segments.